Right? Now let's take a look at this one.
You should have got.
好啦好啦。So this is a side view of the ball. Okay. Don't change my graph. Huh? This is 4D. So here is a radius. This is center of the circle. Now and then it wants you to express the resultant force in terms of W. Now you know it's moving in a circle, so that means you know the direction of oscillation. So point to a center of circle. So that means the force perpendicular to this direction will bounce each other. So in this case,
the center of the circle is very good.
along this line, along this horizontal line. What do you mean? Here, here, or here?
Oh, isn't that wrong? Isn't that wrong?
No. So take a look at the graph here. It's a horizontal circle. Yeah. I know it's quite weird, but it's horizontal circle.
Yeah, is it not just right?
The circle is along this plane.
Have you seen like the game in the arcade where you spin the ball right?
I have quite difficulty to explain it. But if you can't imagine that graph, I can't help. Can you see that this circle is horizontal? Yeah. Then so therefore the center of circle is on the right hand side of the ball. This is a side view, the side view. So if you want to find the resultant force, If you want to find the resultant force, what you need to do is you need to decompose the vector, so the force R, into vertical and horizontal components. So this one is R sine theta, is it? I think last year we spent so much time on which is sine, which is cosine. Is it? Let us see, how difficult is understand. I don't know how difficult. Hello? Don't scare the new teacher, okay? If you don't know. So because the oscillation is towards the center of circle, so therefore the perpendicular directions, the forces, they will bounce each other. And this R sine theta is the resultant force. This is resultant force. In the question, it uses a symbol F. You can write down two equations here. So W equal R sine theta. And then R cosine theta equal to F. And then can you show W equal to F tangent theta? So let's close the door first. Okay? Give some. When she comes, we need some preparation. Okay, some preparation. Are you able to show it?
Yeah. What type of sandwich? What type of sandwich? Peanut butter.
Peanut butter. Oh. For F, okay. I think it's not difficult to show it. If you can write down these two equations. It's not difficult to show the formula. Or just use the first equation divided by second equation. Or whatever lah. It's not difficult to do it. Let's move on. Let's move on.
Sir, that is not very encouraging when you write all that rumble.
Mm-hmm.
And then you just say it's so.
It's difficult. Is it difficult?
可唔可以開始調翻位嘅？
得冇所謂，總之 show 就得㗎啦。係啊。嗯。
Yeah, can you skip all your facts?
有 keep it here.
David's favorite.
This is David's shelf.
In the morning. David always.
Okay, let's move on. So it asks, so state the significance of this force F in the motion. So this force F provides the acceleration for the circular motion of the object. So if this force actually is to maintain the circular motion of the object. The last one. So the ball moves with the radius 14 cm and angle is 28 degrees. Find the speed of the ball. Now, you know you have derived that formula. Find the speed. So F is a resultant force, that is ma. So W is mg. And A can be written as V squared over R if it's a circular motion, is it? The M can be cancelled out. Then you just use your calculator. She's in Dongcheng already, okay? She's coming. Yeah. Be faster. Be faster. Oh. Oh. I didn't eat my breakfast here. Just drink water, okay? Just drinking water is normal. I can't recognize your handwriting. So let's move on to part C. So I say the gravitational potential at the surface of the planet is this value, and find a change in GPE if moving from 6R to 5R. So this is just a potential, but this is just on at the surface of the planet. Now you take a look at the marks, 4 marks. It seems not simple, but indeed it's simple. Ha ha ha. So this value, sorry, this value nav 6.3 equal to nav GM over the big R, is it? Because it's just on the surface. So if not on the surface, let's say 6R, then what you do? Divide by 6, all right? Divide by 6. Now, in your formula, okay, for finding a change in GPE here. So the final GPE is negative GMN over 5R. And then minus the initial. The initial is GMM over 6R. So therefore, GM over negative GM over R is this value. Negative GM over R is this value. Okay. Now, actually, you can see that the physics concept behind is not difficult. Difficult, huh? Find a change in GPE, right? Is it difficult for the physics part? Not difficult at all, right? Not difficult at all. So, and so for this one, for the final GP will be 6.30 times 10 to the power 7 divided by 5 and then times the mass of that object, 1.3. And then minus negative 6.30 times 10 to the power 7 divided by 6 times 1.30. Okay. Oh, dude. So the final answer will be, so yeah, they ask you to find a change. It means the final minus initial. It's always like that. It's always final minus initial. Maybe when the new teacher comes, I will just take a break. And I will move on to the next topic. Not this one. Now, normally the next topic should be the oscillation or the simple harmonic motion. It's a difficult topic, so we move on to the next topic. It's about thermal physics. We can just finish it within 30 minutes. Yeah, almost exactly the same as what you have learned in Form 3. Nothing new at all. Yeah, and also the next cube topic is ideal gas. I think you may have learned some of it in chemistry. Do you? Have you learned about the PAE and NRT? Yeah, quite similar. It's quite similar. But this topic is highly correlated together, just like circular motion and gravitation. Next square chapter and next cube chapter. Next cube one. Next cube next topic. But these two topics are highly correlated together. So can you name one quantity that is the most important concept in this chapter? No. No, that's one quantity that's related the whole topic together. Yeah, that's the temperature. So you say that thermophysics is a study of temperature. Yeah. So then first of all, let's see how we define the temperature. So for temperature, it is defined by thermodynamics First Law. I think she has arrived. Just a second. Now we define temperature by thermodynamics First Law. Now why it seems so strange? Because why the law starting from zero? It's due to history. Because actually there's a first law, second law, and third law. You need to learn about the first law also. And after they have made the three laws, first, second, and third, they find that they forget to define temperature. That's a big mistake. Because you needed the concept of temperature to relate all other quantities together. So later on, they made the thermodynamics First Law. As I remember, this law is around 187 something. Oh, and then let's take a look at how we define a thermodynamics First Law. Now, although in the law, you don't need to learn about the details of this law in your syllabus, but just tell you how to define it. So in this law, it says that if A and B are in thermal equilibrium. In chemistry, you have learned about a lot of equilibrium, do you? Chemical equilibrium. So what does it mean by thermal equilibrium? So that means when they touch each other, there's no heat or energy transfer from one to another. Then that means they are in thermal equilibrium. So if A and B are in thermal equilibrium, and if B and C are in thermal equilibrium, then A and C are in thermal equilibrium. You may think that, okay, this law is so dumb. It's so obvious, is it? It seems it's so obvious. If A and B and C are in thermal equilibrium, the A and C must be in thermal equilibrium. Do you think it like that? But in science or in science and especially in physics, we need to define everything carefully or precisely. So let's say, let's three people here. So let's say I'm a friend of Oscar and I'm a friend of Sweeney. Does it mean that Sweeney and Oscar are friends? No, they are not friends. Maybe. So that's why we need to define like that. Now you may also ask about how it is related to temperature. So temperature is the common properties, or these three objects, they have the same temperature. There's one quantity that these three objects have in common with the same value. That is temperature. So they're in thermal equilibrium. That means they are at the same temperature. So in other words, okay, thermal equilibrium, it means same temperature. So that's the thermodynamics First Law. And then later on, let's move on to the first law. Hi. But the year that they made the law. Oh, let's move on. So then let's go to the first law, thermodynamic first law. Now, actually, it is equivalent to conservation of energy. So, and then let me write down the formula. So this is the formula for the thermodynamics first law. So this formula is talking about the energy of an object. So this one is a change in internal energy. Do you still remember how we define the internal energy? Yeah. So you have learned it in Form 3. I think that, okay, and also you have taken the GCE exam. I hope you still remember. So this is a total sum of, sum of total, okay? So this is sum of total kinetic energy, the total molecular kinetic energy and potential energy due to random motion. And I would like to explain what is meant by molecular KE. So you see that, okay, you can see that I'm moving here. So every single molecule in my body is moving. But we didn't count that KE. So you know the formula for KE is half mE squared. So you don't use half times mass of Mr. Young times the speed square of that I'm moving. So that's not the molecular KE. So for molecular KE is you take a look at each single molecule and find their speed, and then count the molecular speed. Molecular KE, the KE of the molecules one by one, and then take a sum. So let's say there's so many molecules here, and then you will find the speed. You're finding their KE individually, and then take a sum. That is a molecular KE. If you're moving them as a whole, you don't count that KE. Understand? Let's say if you're moving a box, you do not increase the internal energy. You do not increase the internal energy. Because the speed of each molecule. Okay. Oh, okay, sure. Because the kinetic energy of each object, the kinetic energy of the whole, each molecule does not change if you move the box as a whole. So another one is about potential energy. So for potential energy, so you know there's different states in a molecule. So there are solid state, liquid state, and gas state. So which one has the highest PE? Gas state has the highest PE. Oh. Then also let me define Q and W, okay? But there's a lot of the questions in the past paper, they ask you to define what's W and Q and change in energy. So for Q, it is a heat into the system. You do not just mention heat. So because it can be the heat supplied by a system or by a system. And on the system, there are different things. The heat in the system, that means the system gain energy by heating. And if the object lost energy, so let's say there's 100 degrees Celsius water here. So most likely it will lose energy by conduction or radiation to the surrounding. So then in that case, the heat will be negative. The Q will be negative. Negative. If you put the fire on it, then heat will be positive. Okay? So W is the work done on the system. But this formula is actually not difficult to understand. So let's say I have a water bottle here.
Sir, can I use it for
Huh? Sure.
Can I just do it on the chest right there? What?
Now,
So the sound waves and the internal pressure.
okay. Let's move on. So I have a bottle of water here. So I'm so warm, you know, I'm very warm. So when my hand touches the bottle, the water is heated up. So the internal energy of the water increases because of my heating. And also what else I can do? I can do work done on the bottle of water. So I can just shake it partly. Most likely, okay, if I shake it maybe 1 hour, for 1 hour, the temperature of the water will increases. You do it. Well, just like you rubbing your hand, there's work done by a friction, and then your hands get warm. So there's only 2 ways to increase the internal energy of an object. So either you hit it or you punch it. That means you give the work done on the object. So that's why I say that it's same as the conservation of energy. It's just another formula, another form of conservation of energy. Okay. Later on, we will take a look at the formula of heat, work done, and change in energy separately. So then let's move on to the heat. I'm not sure if you still remember the formula you have learned it in Form 3. So for heating. So there are 2 formulas. So one is Q mc del T. So in GCE you use a symbol Q for heat. So this is the energy. So this tells you how much energy you need to heat an object with the mass m to change its temperature del T. So that's a formula of heat. And then there's another formula, is it? Yeah, QML. So this one is the energy required to change the state of object with mass m. Or there's another term for it, it's called the latent heat. Now you may be asked to define the L and C in the long questions. So C, you know, what was the name for it? Specific heat capacity. But the word specific, it means per unit mass. So this one is a specific latent heat. So specific heat capacity is defined as the energy provided to object with mass m. I don't know. So the energy required to change 1 kg object by 1 degree Celsius. Why I'm so dumb? And then for specific heat, so you know this is energy required to change change the state of 1 kg object. And you also need to mention that without change in temperature. You know when the object is changing a state, the temperature is kept constant. Hola, we finished the half of the chapter thermophysics. Oh yeah. Very good, very good. Oh yeah, very efficient. Now let me also draw a heating curve. So let's say if you're heating, let's say 1 kilogram 0 degrees Celsius, sorry, negative 10 degrees Celsius ice, and then I want to draw the temperature against time. Good. So temperature against time. So you know the ice first will increase its temperature until 0 degrees Celsius. And then the ice will start to melt. Is it? After all the ice melts, it becomes 0 degrees Celsius water. And if still keep heating, the temperature increases. So the graph will look like heat. But if you still keep heating it and then it becomes steam, that means it's changing state at 100 degrees Celsius. And then it will become until all the water becomes steam, the temperature still remains 100 degrees Celsius. Then. So if and then it will increase its temperature furthermore. Now, why I draw this graph? Because I want to remind you when you should use the formula mc del T or ml. So for the formula mc del T is for the part when the object changes its temperature. So that means it's only for a part when the object remains the state solid, liquid, or gas. And if you're using ml, it's the part when the object changes its state. So that's the part when temperature kept constant. Okay? I think it's not difficult at all because you have also learned it in Form 3. So this is the path solid to liquid, liquid to gas, and then gas. Oh. Done. It's almost the same as what you have learned in Form 3. So let's move on. Hi. Hold. Now we finished talking about the heat scalar. If you're so there's two different heating methods. Oh, sorry. Either you change the temperature of the object or change the state of the object. So then let's go to the work done. There's actually one formula for the work done. Now in this talk, you know, in the next topic, we are talking about the gas, ideal gas. So we are talking also need to learn about how to find the work done on the ideal gas. So let's draw a center. So this is a piston. Good. You think about light as a range. You can push it. When you push it, that means you are doing work on the gas. So and then we want to find that work done. Oh, yeah. This is a closed container. There's no gas leakage. Now, if I push it with the distance s, I hope you still remember the form, the definition of the work done. Then the work done will be F times S, is it? We push the piston with the distance S. Then work done will F times S. But we, to describe the gas, I think you learn it in the next chapter. So normally we use a pressure, volume, and temperature to describe the gas. And then we need to relate the force to the pressure. A constant force F. Let me write it down as a constant force F. So you have let this area to be A. How can the force relate to the area? You learn it in GCE. Now pressure, force over area is the pressure. So force can be written as pressure times area. So this is a gas pressure. How about A times S? A times S is the volume, is it? It's a volume here. It's a volume here. A times S is a volume here. I will write it as negative change in volume. You know that this triangle, it means change. So V is volume. So this negative change in volume. Can you tell me why it's a negative sign here? Yeah, because the volume is decreasing. So in this case, the volume decreases. The change in volume will be negative. The change in volume is negative. So I put a negative sign there. Maybe let me write here, okay? So work done, you have a one formula, it's negative pressure times change in volume. So if the volume decreases, then the change in volume is negative. If the volume increases, the change in volume is positive. So if the volume decreases, how about the work done? Is it positive or negative? If just looking at this formula, then it will be positive, is it? Because this one is negative. Negative times negative will give you positive. So then in that case, the work done will be positive. So how about if the volume increases, then the work done will be negative. So what does it mean by positive work done? That means you increases the energy of this gas or this system by work done. So you think about it, if you push the piston, the volume decreases. Do you do work on this system? Do you give energy to this gas? Yes. So you increase the energy of this system. So therefore the work done is positive. Okay, so we have this formula. And actually I want also to, if you think carefully, when I derive this formula, I assume that the force is constant. So what happens if the force is not constant? Or I think you have also experienced this when you push a syringe. The smaller the volume, the more difficult you push, or the harder you need to push it. The force is indeed not constant in that case. Yeah. But in your syllabus, okay, to find the work done for this formula is only for constant pressure. This form is only for constant pressure. If the pressure is not constant, then you cannot use this formula. But this formula is only for constant pressure. If the pressure is not constant, how can we find the work done? We can just use the Thermodynamics First Law. So that is, now we can just go back to use this formula to find the work done. If you're given a heat, and also if you are given the change in energy, then you can find work done. Okay. Now let me ask you another question. So you can see that when I derive this formula, I said that this is a gas. How about it's a liquid? How about it's a solid? Now, in most of the case, we will just ignore the work done on the solid or liquid. Because if you think about the form, if you still apply this formula, let's say this is a water. I know there's some gap here, okay? There's some gap here. So let's say there's some solid, your phone. Okay. Can you actually change the volume of this phone easily? No, is it? So actually, you can difficult to change the volume of a solid. Okay, and also the liquid. So we ignore the work done on the liquid and also on the solid. But on gas, we cannot ignore the work done because you can really change the volume of the gas. Easy. Okay. And also let's take a look at the formula. So I draw some diagram here, and then you try to find the work done on the gas. So this diagram shows you how the pressure changes with volume. And then you think about the formula of the work done. So first of all, in those diagrams, it will show you the arrows. So that means the gas is changing from this stage to this stage. So you can see that the volume increases. And how about the work done will be? The work done will be positive or negative? Negative work done. Here, the work done is negative. So when you write down the formula in terms of the P, V1, and V2, actually you just don't need to think about it, whether it's negative or positive. You just substitute in the formula. So a change in the work volume will be V2 minus V1, is it? Because it's always the final volume minus the initial volume. So it's always V2 minus V1, the final minus initial. So if the gas is moving from V2 to V1, then the work done will be negative P times V1 minus V2. Okay? Because in that case, V1 is the final volume, V2 is the initial volume. 好，我哋繼續。No, I said that, okay, I just lazy to draw a graph. So for the red arrow, it means it's changing from this stage to this stage. The volume changes from V2 to V1. Then the work done is that formula. So you see in my diagram, the pressure is constant. So therefore the graph is like a horizontal line. So if the pressure is not constant, how can we find it? So let's say it's like this, okay? Oh, of course it will not be that ugly, okay? In your exam, or just like this, it will not be that ugly in your exam. Now, other than using the formula to find the work done, if the pressure kept constant, if the pressure is not constant, and then you're given a graph, you can actually find the area. The area under the graph means the work done. So what you do is just finding area. But the differences between these two is, so this one, the work done is negative because the volume of the gas increases, or just say the gas expands. But this one, the gas contracts, so the work done is negative. Sorry, so the work done is positive here. So it's kind of positive area. Now, you see that, okay? We finished the topic of thermodynamics. Sorry, thermophysics. No. Almost. There's one more thing in that chapter. But you know about that already. You know about that already. But the last thing in this chapter is, I think you still remember it. Gua. So do you know what is the lowest temperature? Hmm? Yeah, it's called F.0. So that value is -273. That's what you remember in GCE. But in A level, you need to remember -273.15 degrees Celsius. Hi. And do you still remember how to convert the degree Celsius to Kelvin? This is still Kelvin. Do you still remember? Is it? Yeah. So temperature in degrees Celsius, if you want to change it to Kelvin, you plus 273.15. Then you change the temperature back to Kelvin or Kelvin to degrees Celsius. I hope you still remember it. But indeed, okay, in your calculation, you can just take 273 only because you know almost all the values given in the question will be in 2SF or 3SF. It actually doesn't matter if you take more SF in the temperature. Oh. In the chapter of thermophysics, actually there's some other there's another part is about the thermometer. I'll leave it to the teachers to teach. Yeah, that's the part of thermometer. No, there's only the part of thermometer left in the thermophysics.
Oh,
yeah, this is thermocouple and yeah, it's just some factual part. Just factual part. No, not difficult at all. No, not difficult at all. No, but actually in the past period, they seldom test that part. Hold up. Now I just want to introduce a bit about the ideal gas law. Then that's end for today. So can you tell me what you have learned in what you have learned in chemistry about the ideal gas law? Ideal gas law. Ideal gas law in chemistry. Mole calculation for gases, is it? You find how many mole of gas, let's say for you are given, let's say 44 dm cube, and then you know it's around 2 mole in chemistry. You take chemistry, you know about it. So in chemistry, it's 22.4 dm cube, is it? Right. Forgot how many? 22.4 dm cube, is it? Chemistry. For molar volume. 24. The difference between 22.4 and 24 is the temperature. So you say like in chemistry, you know the formula for ideal gas law. So that is PV or nRT. If you didn't study chemistry, it doesn't matter. So we talk about this formula first. So this formula, we call the ideal gas law. This is the law for ideal gas. I'll talk about what is ideal gas a little bit later on. But let's take a look at this formula. So N is the number of mole. This is time to test your chemistry. How do we define 1 mole? I know the value. I know the value of 1 mole, but What is the definition? Definition. Hmm?
On the carbon buzz scale.
Yeah. So there's the number of atoms of 12-gram carbon 12. So there is 1 mole, 1 mole. You need to know this definition in physics also. Yes. Yes. Carbon 12. You can just write down this symbol because you have learned it in physics also. You learn it in the topic radioactivity. What does it mean? You have learned about it already, is it? I'm sorry. Now then the value is called Avogadro constant. I don't know how to spell Avogadro, but for symbol we use Na. So it's 6.02 times 10 to the power 23 number. So for R, so it's called the gas constant or universal gas constant. The value is given in the form sheet and also in your calculator. It's 8.31. Do you need to know this value in chemistry? Yes? This one. Shift 7, 4, 3. There's some unit here, okay? I'll just ignore the unit. So T, this is a temperature. Now remember the temperature should be in Kelvin. If you use degrees Celsius and then you get everything wrong. You get everything wrong. The P is the pressure, V is volume, nothing else. Now in chemistry, let's say for the 24 dm cube, you know how to derive it from this formula. 24 dm cube, you know how to derive it from this formula. P is the pressure, V is the volume. So when can you use 24 dm cube? 1 atm at which temperature? 25 degrees Celsius. Now let me make the volume be the subject of the equation. So nRT divided by P. So in chemistry, you have this concept. So for 1 mole of gas at 25 degrees Celsius, remember you need to change it back to Kelvin. You learned how to change it already. Divided by the pressure. Now, there's 1 atm. In physics, given the value. There's around 1.01 times 10 to the power 5. Then you check it with your calculator. 1 mole. So the So you will get around 24 dm cube. But actually I don't know why I always get 25 dm cube if in 2SF. Like in chemistry, 1 meter is 10 dm. 1 meter is 10 dm. So you need to multiply by 1,000, then you can get Kelvin, in Kelvin.
Yeah, Calvin is in.
It must be in Kelvin.
Yeah, I know. But like, is the reason why if you round to significant figures, you get
No. Because 24 dm cube is measured experimentally, it's not theoretically. 好啦，now then tomorrow we just go on to talk about the ideal gas number. Yeah, and I hope we can finish the next chapter tomorrow. 好，I see you all tomorrow 啦。Yeah.